Okay, so what we have here is a Punnett square. I'm assuming you guys have heard of Punnett squares before, right? Okay, so as we look at this, without like needing to know too much about biology, you're also kind of told here that based on the Punnett square, we have these tobacco plants. I think they're tobacco plants. Yes. Okay. And the colors of this tobacco plant, it can either be green, yellow-green, or albino. And green being dominant, yellow-green being where you have one dominant, one recessive. Everybody good? Okay. So I might look at this and I might say my null hypothesis is that the proportion of green should be 0.25. The proportion of what I'm going to use PY to represent yellow-green. And that should be 50%. And PA to equal 0.25. And my alternative to that is at least 1 of the P sub i's is incorrect. And with P sub I equaling true proportion of plants in that color. So if P sub I, if it's PG, it's green. If it's PY, it's yellow-green, etc. And in some respects, I might look at this and say, hey, the minute my null hypothesis is really about 3 different proportions, the appropriate test for that is a chi-squared goodness of fit test. Now, what was my first condition of the chi-squared goodness of fit test? Random. And is that condition met? What's the next condition? Large sample size. For that large sample size, we would need to figure out, well, what are my expected counts of each? Okay? So for the green, it would be 0.25 times 80. For the yellow-green, 0.5 times 80. Albino, 0.25 times 80. You get 20, 40, 20. Those are both greater than or equal to 5.
Why did you use 80?
Because that's, a wonderful question, and I should not have. Sorry, I was using. So then that would be 21, 42, and 21. Everybody good? Independent, 84 is less than 10% of all tobacco pairings. Great, now what? Run the test, okay. So I'm going to go into my calculator. Remember, we'd like to put the observed in L1 and the so in L1, I'm going to put, well, how many green were there? So let's see, we got 23 green, 50 yellow-green, 11 albino. And again, what I would do is somewhere write a note to myself just to be on the safe side that I have my observed in L1, my expected in L2. Okay. Just so in case I'm misremembering which one my calculator's asking me for, right? Okay. So then I hit set, I go to and I'm going to pick the chi-squared GOF test because we need to do a chi-squared GOF test. That's our procedure. It asks us for where am I observed, where am I expected. What's my degrees of freedom here?
83.
I'm sorry?
83.
That is incorrect. My degrees of freedom is 2. Remember degrees of freedom in this case is about how many values are going into chi-squared, which is 1 for each category. It's your categories minus 1. Okay? So 3 minus 1 is 2. I go down, I hit calculate. So I can see my chi-squared value is 6.47. My p-value is 0.039. And for green, my contribution was 0.19. Yellow-green, it was 1.52. And albino, it was 4.76. In this case, my p-value is less than alpha. So we can reject. No. We have enough evidence to say the proportions of each color are different from notice you guys, I'm stealing the language from above. I always try to use the language written in the question of the differ significantly from what the biologists have predicted. So that's the verbiage I'm using in my conclusion. All right, now, as we go through for this next part, the question becomes, if once we have a significant result, we might be asked to do some sort of follow-up analysis. Because remember, our alternative, we're saying at least one of these proportions is wrong. And so then we got to decide, well, if it's at least one, probably 2. But if it's at least 1, which one is it? Okay, and as I'm looking at these, this is where those contributions that are coming out here, right? This is where these come into play. Because these are that observed minus expected squared over expected for every category, right? And so as I'm looking at these, which is really these numbers, right? And that was where I got these from. Which values contributed the most to chi-squared? The albino. Right? Like when I look at this is a much larger contribution than the other two, even the other two combined. Is everybody good? Okay, so if I were to ask you which proportion was wrong, it's the proportion of albino is not what we would have expected. Is everybody with me? Now, what this value does not tell me is if I'm going to say, yep, the albinos are different from what we expected, but that's not a great answer, right? Because really, we wouldn't want to just know, okay, it's not equal to. We would want to know, how is it different? Is everybody good? So I would start this follow-up analysis by saying albino plants had the largest contribution. And in this case, our expected was 21. And what actually happened was 11. So when I say the proportion of plants that were albino is the one that's incorrect, how is it incorrect? It's lower because we got less than we expected to get. Is everybody good? So it is likely, I might say that likely that P sub A is actually less than 0.25. I'd feel pretty comfortable there. I'm not sure I'd be comfortable saying which of the other two was bigger, though certainly it appears like it was coming from one group more than the other. But we typically look at where do we see big separation between the contributions? And that one is significantly higher than the other ones. Everybody good? So one, you want to start with saying, hey, which one contributed the most? Then follow that up a little bit more with what does that mean? And what you want to do is make that comparison of, did we get more than expected or less than expected? Yeah.
What's the limit for being able to make a conclusion like that? Is it like thousands?
The minute you get so there's not like a set rule of thumb. Okay, so, and first of all, we'd only do this if our p-value was smaller than alpha. If we aren't concluding a significant difference. In this case, like that 4.7 is way bigger than the other two. Sometimes it might be like you might have two that are really big and maybe mention both of them, right? It's just it really is case circumstantial based off of the examples. All right. Questions? Are we feeling pretty decent about goodness of fit tests? Okay. And so some key things, because I'm about to shake up chi-squared a little bit more. Some key things that tell me goodness of fit is I have a singular list of proportions and a singular list of a lot of proportions. Everybody okay? Now, the next set of chi-square tests we're going to do is going to be on two-way tables. So what we're going to do is I'm going to do a quick review of two-way tables. We'll take a break, and then we'll start the chi-square test for association and the chi-square test for homogeneity. Okay? All right, so I'm going to let you guys read this real quick so that we're all on the same page. All right, so first, pretending this is the AP exam, and I asked you part A, is this an observational study or an experiment, and explain. What would you write down? Experiment. Is that all we would write down? The musical treatments were randomly assigned. And for where we're going to be going with this, who were they randomly assigned to? a group of volunteers. So at the end of the day, if we end up with some sort of significant result, what will we be allowed to conclude? We have random assignment of treatments, but we do not have a random sample. We can conclude cause and effect from the random assignment, but we can only conclude it for people like those in the study because we don't have random selection. Everybody good? All right. Next. Why was there a group that didn't listen to any music at all?
Because it could have been chance. And one, if the jazz or the classical did better than the other.
So we're going to talk. No, but I want to hold on to that idea for after break when we start doing the next step. Because the idea of could it be chance is an important one. Bruno, what are you thinking? Okay. So if this were the AP exam, that would be a great start, but we would want to do a little bit more. What does this group control for? For starters, it could give us an idea of what percent of students would complete this assignment with or without music, right? Like it gives us is the music helping versus is it the type of music versus is it just music? Is it just maybe we could, because this could have been a white noise group, right? Where we had like a white noise machine doing like the sound of rain, or you guys get what I'm saying? Okay, so when we talk about a control group, what we want to do is talk about the information we get from that control group that we wouldn't get if it wasn't there. Is everybody good? So if any music influences assignment completion, versus no music at all. So maybe it's not the type of music that matters. You guys get what I'm saying? Maybe it's, right? So if the treatments are the different styles of music, but all music helps and versus none, that's an important thing we would want to see. And lastly, real quick, y'all, if I asked you what is the probability that a randomly selected person from this group completed the assignment, what would you say? I'm sorry? 80 out of 150. Thank you. So we would expect, in general, a little over half of each group to complete the assignment. All right. Next. What is the probability that a person who listened to jazz music completed the assignment? What would that be? That would be we know that they listened to jazz, right? So to me, that would be what is the probability they completed the assignment given that they listened to jazz?
23 over 45. 0.51 repeating.
Then, because I'm going to make you guys do this down here anyway, but when I'm asking of complete the conditional distribution for each treatment group, we're going to write it up here so we have more space for the graph down here. Okay, so what about if they listen to classical? That would be 31 out of 54, right?
0.574.
Now, the second part of this are the events independent. So trying to decide if any two events are independent. So the probability of completing the assignment was 0.53. The probability of completing the assignment given you were listening to jazz music was 0.51. Technically, for what you guys know right now, these two events are not independent because people who were listening to jazz were slightly less likely to complete the assignment than overall. In order for the two events to be independent, these two things would need to be identical numbers. They are not. Is everybody good? So, based on what we know about we would say these two events are not independent because the probability of completing is bigger than the probability of completing given jazz. The two probabilities those two probabilities would have to be the same. And if I were asking you about just the 150 people in this sample, this would be 100% the right answer. Now, to pull back, Charlotte, what you kind of said of like, it could have happened by chance. Do we all agree in how we think about samples and that this was a sample of 150 people? And what do we know about samples? Samples are not perfect, right? And these are definitely, they are different, but are they? Are you guys with me? This might not be enough to convince me that that difference is significant, is meaningful. So if I'm asking you about specifically just this group of people, they are not independent. After break, we're going to talk about the test for deciding are those differences big enough for us to be convinced that it's a major difference or not? Is it significant or not? Okay. The last thing I asked you guys to do here is after finding that conditional distribution, which we kind of did, okay? The next thing we're going to do is draw an appropriate graph to compare. The appropriate graph I would use to compare here is a segmented bar graph. I have 3 different treatment groups. So we're going to have a bar for jazz. We're going to have a bar for classical. We're going to have a bar for no music. And my horizontal axis will be the relative frequency of completion rates. Or completion status, I guess, would probably be the best way to do it. New reminder with a segmented bar graph. So for instance, the jazz group, I'm going to draw the segment at where I believe 51% is. And then for the classical group, 57. Sometimes we use different coloring here, however you want to do it, okay? And as I'm looking at these, we can begin to see, like these two groups are practically identical. There's probably some slight differences in rounding, right? Where we can see this one's a little bit further over. right? So if I were to be looking at this right now and I've decided I need to go get some work done, if I'm looking at this data, I might choose to listen to classical music while I'm studying or while I'm doing whatever it is I need to get done, because it has a slightly higher completion rate. Now, what questions do we have so far? So if I were to talk about what are the big ideas, this concept up here of when two events are independent, what makes two events independent is that whether or not the second event occurs does not influence whether the probability of the first event is going to occur. Okay? This was a huge concept that came out of Unit 4. Okay? Probably one of the most important big conceptual ideas. Okay? And what happens if I'm trying to decide if event A and event B are independent, a lot of times students try to compare the probability of A to the probability of B. That has nothing to do with independence. It has to do with, if I know that one of them has occurred, has that changed the probability that the other has occurred? And one of the pictures I tried to draw for you guys here is like essentially the different fractions and whatnot that we're working on. The different fractions, like if we think of, we're comparing for every single one of these graphs, we actually created the same fraction. Okay, all of them were the proportion of completed, and we want to be comparing similar fractions each time. So in reality, we chose, for instance, these two, these two, these two, and these two, all comparing the fraction of the same thing, just for different groups of people. And that's how we determine if two events are independent. Is everybody good? And then lastly, a real quick vocabulary refrain. So when this happens, we say the events are independent. And if two events are independent, there is not an association. If we have that the probability of A is not equal to the probability of A given B, we would say that they are dependent. And if two events are dependent, another way we might say that is there is an association. So I just want to make sure we're all on the that language thing, because we're going to jump into a whole bunch of that after the break. Independence and association mean the exact same thing. Questions so far? All right, in terms of what is a good stopping place,